Let's see, we got a lot to get through, and I haven't timed this yet, so I don't want to make sure we all get it into our allotted time frame. Two-dimensional experiments. So it's one thing to do things in a column with a very confined geometry. But of course, when we go to do in situ star in the field, the reaction is going to be propagating in multiple dimensions. And there's virtually no research that's been done on how a smoldering front could travel in multiple directions at once, not just upwards, but also outwards. And so we really wanted to start to understand how star could propagate in multiple dimensions at the same time, and how that would affect the propagation of the front. So we developed a series of experiments to explore. It's basically the same thing that you've seen before, contaminated soil, a heater, but the heater only occupies a fraction of the material. And the airflow also can be applied across a fraction of the material. So picture now something similar to a well being put into a coal tar contaminated site, heating in that well and also blowing air into that well. And how would the front propagate outwards from that well? How fast would it propagate vertically upwards? How does that compare to our column experiments? And also, what kind of lateral propagation do we get? Basically, what we want to know is what kind of radius of influence, ROI. Every technology that's delivered from a well has an ROI, a radius of influence, and we want to try to start understand what affects the radius of influence of star. So we're studying the rate of vertical spread, the rate of horizontal spread, and where that extinction boundary will occur and what will control that extinction boundary. We're also looking at the rate of downward spread. I haven't talked about this much, but when you smolder any kind of solid, charcoal or polyurethane foam, you actually can have the reaction propagating in the opposed direction to the airflow. So airflow is going up, but the reaction actually can spread downwards. I'm not going to get into that today, but basically we've proven that for smoldering of liquids, that doesn't happen. So it's a unique feature of star that you will not get propagation of the front counter current to the airflow. All the reaction happens at least in some direction parallel or in conjunction with the airflow. So that's an important point. Okay, so we develop a sandbox that looks like this, about 40 centimeters wide and about 20 centimeters tall. And every other way, it looks basically like the column I explained to you. We have a diffuser, some pipes where we inject air, but only over a 10 centimeter, I think maybe a 13 centimeter width on one side, and the rest of it has no airflow. We have an igniter, same as we had before. We have our thermocouples that are immediately above, in the vertical array above the igniter and diffuser. So this is similar to our column. But of course, we have an array of thermocouples out to the side to look at horizontal propagation. And this is what that experiment looks like. You can see all the thermocouples going into it from the top. You can see we've got insulation around the outside because we want to minimize heat losses. That's standard for combustion experiments because we want to mimic what's going on out in a site. And in a site, there would be contaminated soil all around here acting as insulation. So this mimics that. And you see we have a layer of contaminated soil above some clean soil here and some clean soil here. And we're going to be looking both at these vertical thermocouples and also at the thermocouples out to the side. So here's a base case experiment. And here's what the thermocouple profiles look like immediately, basically in that first array of vertical thermocouples basically above the igniter, but at the edge. And you can see we're getting a self-sustaining smoldering reaction, peak temperature of 800 degrees. This is coal tar in sand, very similar to what we've seen before. The first line is the air on, when we turn the air on, and the second line is when we turn the igniter off. So we get the self-propagating reaction, and we get really good cleanup, full remediation immediately above the igniter. Now, as we move to the next set of thermocouples outside of the ignition zone, we see that the lowest thermocouple, there's ignition here. You see this sharp rise. You definitely get some ignition, but a lower peak temperature. And then for the rest of the thermocouples, we get basically very similar behavior. Again, as we move further away, this becomes more pronounced. We have this rising peak of temperature. And again, as we move even further away, now we're not getting very strong ignition. We're getting some heating. This is a heating, but not very strong ignition. And we're not even seeing 500 degrees as a peak temperature. And we're not getting these overlapping peaks that we associate with sort of an exothermic propagating reaction. So as we get further away, we're seeing something different occurring. So what we do is, to actually see what's clean and what's been remediated and what's not, we excavate. And here you can see we're excavating from the top downward. So we see a very distinct clean zone. The igniter is right in this location here. And we see this wide clean zone at the top. And as we excavate downwards, so we're excavating in 2 centimeter lifts, we see that the clean zone is getting smaller and smaller until we get down to the igniter itself. We see a narrow clean zone right around the igniter itself. Okay? So basically there's an upwards cone, and here's a cross-sectional profile. This is our excavated measurements along this red line. So you can see that we're showing only half the igniter here. We're showing the right half of the box, basically. And you can see that there's this upwards curving profile, which you would sort of expect, because you can imagine that the air is being blown into this zone, and it's traveling upwards and outwards, and the smoldering front is somewhat matching that upwards air injection profile. And the unremediated zone is in this zone here. So that's interesting, and partly what we expect to see. But we have this, so we don't, in the column we had, if you recall, something straight up here. So we're getting all of this extra zone remediated in this two-dimensional configuration. So let's see, we have, now what I want to show you is that we have this profile here, and I'm going to look at 2 points in particular. I'm going to take one location where we had a thermocouple, and we had a soil sample from the unremediated zone, and I'm going to take one from inside the remediated zone, and I'm going to compare them. In particular, what we're going to do is compare their temperature time histories, so we can understand better what's going on at those 2 locations. So the red line is this point here that was completely remediated, and you can see we have a very strong ignition reaction, a peak of 800 degrees, and a drop-off as the front passed that location and it started to cool. At this location here, it was at the same height but further away, you can see we had some heating. So there was some heat gets propagated in 2 ways. There's convection and there's conduction. Right? Convection is a flowing transfer of heat, and conduction is the propagation of the heat through the solid. So it got heated, but not really a strong, you don't see a combustion reaction. What we see is a heating and then a cooling. Now, what we're doing here is what's called a thermal severity analysis. So it's a very interesting type of analysis that you can do on these data. And what we do is we try to estimate, we don't try, we actually break this temperature regime into 50-degree increments, and we classify each location by the peak temperature it reached and how long it spent at that peak temperature. So, for example, here's the 2 peak temperatures. This one reached 801.5 degrees. This one reached 342. And since we're looking at 50-degree increments, we can say that this thermocouple, this location, reached 800 degrees for almost 1 minute, but did not reach 850. Okay, so it reached 800 for 1 minute. This location here reached 300 for 14 minutes, but it did not reach 350. So we would classify this point as 300 for 14 minutes, and this point as 800 for 1 minute. And what we then do is we take those 2 data points and we plot them on a severity analysis profile. This is temperature, peak temperature reached in Celsius, degrees Celsius, and this is the time spent at that peak. So you can see here's the one location, 1 minute at 800, and here's the other one, 14 minutes at 300. And what we do is we take all of the all of the temperature profiles from that, not just that experiment, but from 6 different experiments that we did, where we vary different factors, and we plotted them all on one plot. And this is what you get. You get basically a curve like this. So here's all the unremediated points, and here's all the points from inside the remediation zone. And what we see is that there's a very distinct line between the 2. And what it shows us is that if you have a location that experiences basically 600 degrees here for more than 1 minute, then we can expect that the front has remediated that location. Or you might have a location that experiences 550 degrees for more than about 4 minutes. Or you might have a location that experiences 700 degrees or 800 degrees or 900 degrees for any amount of time whatsoever. But if you have a location that experiences 500 degrees only, it doesn't matter how long it spends at 500 degrees, it'll never be cleaned up. So it gives us a very nice definition of using thermocouple profiles to know where the front is and to know where the line is between remediated and unremediated soil. So, for example, we take this criteria, this thermal severity criteria, as 600 degrees for 1 minute. And we say wherever we see in our experiments, or even in the field, if we see 600 degrees for 1 minute, we're pretty convinced that, at least for coal tar, now this is explicit for coal tar, and probably this is different, in fact it is different, for different fuels, different contaminants. But for the moment, let's focus on coal tar. If we're doing a coal tar site, which I'll show you in a little while, when we see 600 degrees for 1 minute, we can be pretty sure that that soil is clean at that location and the front has moved onwards. So now what I want to show you is all of the data from our base case experiment plotted just with respect to that one criteria. So blue triangles are locations that have not exceeded that criteria. Red circles are currently exceeding that criteria, and green squares had exceeded that criteria, had exceeded 600 degrees for 1 minute, but now they've cooled down. And so at 5 minutes after we've turned on the air, you can see that our front is somewhere in this region here. You can see all of this is still cool. The front is here, and this area has already combusted and starting to cool down. And as we march through time here, you can see the front expanding in time into the unremediated region. So now you see the front is up here. And I think this is my last slide, where now you can see the beginning of that treatment area in time. You can see here's the treated zone, and here's the untreated zone. And you can see how that's developing outwards as a sort of mushroom. So that's very interesting. That's never been observed before. Here's our final slide. And then you can see this is the line I showed you before. We have the excavation between the remediated and unremediated zones. And here it is again. When everything cools down and we actually excavate, we can compare the points on this side of the line that never got remediated, never exceeded the criteria, and those on this side of the line that did exceed the criteria. So it's a really important study for us because it's the first time we've been able to use, because remember, this kind of excavation only works at the end of the experiment. But now by using this thermal severity criteria, it's for the first time we can analyze during an experiment where the front is. So here we're going to plot average forward velocity. Now this is the same as we looked at with the column experiments. This is the forward velocity going straight upwards out of the reaction zone as a function of airflow rate. We've now done 6 airflow rates. And what we see is, again, a very strong linear relationship. Same as before, when you increase the airflow rate, then the rate of upwards vertical propagation velocity is increased in a linear fashion. We also see now that we did an experiment where there was a low airflow rate. This is down to 25 liters per minute. 50 liters per minute produced a self-sustaining reaction. 25 liters per minute didn't go anywhere. Nothing got cleaned up. It did not produce a self-sustaining reaction. So there is a minimum amount of air you need to push. And that makes sense because the stoichiometric reaction, whatever it is, requires a minimum amount of oxygen before it ignites. So that's interesting. And also it's interesting to see the same pattern as we see in the column experiments. Now we're talking about, that's upward velocity. That's moving basically up this way here. Now, how about this remediated zone? How about the lateral propagation? Well, it turns out it's also sensitive to air injection rate. Here's the 50 liter per minute clean zone. You can see basically the reaction went straight up and we had no horizontal propagation whatsoever. Basically looks just like a column experiment. We increase that to 125 liters per minute, and we start to get some lateral propagation here. 250 liters per minute, and we get a much wider clean zone. So it makes sense that as you're increasing your airflow rate, you can have a larger radius of influence around the ignition zone. However, as we continue to increase the flow rate, 350 liters per minute, 450 liters per minute, now we're starting to get very little further effect. It's increasing, but not much. So the effect is nonlinear. We have large amounts of increase of radius of influence for small airflow, for at the lower end of increases of airflow rate, but at the higher end, we're getting very small effects. And further analysis shows that we are having some boundary effects here. As you know from the modeling, you can have a boundary effect. We're having air, the airflow rate is being affected by this lateral boundary here. It's possible that if this was wider, then these larger airflow rates could have pushed this out to an even wider radius. Okay, so to conclude from the 2D experiments, what do we see? We see that the front propagation is controlled by the pattern of airflow and the rate of airflow. So, if you were to inject your air in a different manner, it probably could change the pattern of propagation. Certainly the rate of airflow is shown to be a critical parameter. We see that there is some energy balance. I didn't talk about that too much, but when we have that reaction front here, basically this is an extinction front. There is a balance of energy going on here between the amount of energy produced, the amount of energy carried forward, and the amount of energy being consumed. And so there's an extinction front here. And as we change the airflow rate, we're changing that balance, that energy balance. So we're pushing that reaction front outwards, the extinction front outwards. We see that the shape is kind of similar to an air sparging pattern. So if you air sparge from an injection well, you get a spherical pattern that grows outwards from the well, and we're seeing a similar pattern. What I'll show you later is that you cannot simply predict where the airflow would go from air sparging and assume that's the area that you would clean up. It's not exactly the same thing, and I'll try to explain in another section why that is. We see that the thermal severity analysis is a very useful tool, and using it, we'll be able to generate a criteria where we can track in time where the front is, basically, between the partition between the remediated and unremediated zone, so we can track that in space and time. We see that upwards propagation, just like the column experiments, is linearly dependent on airflow rate, and that lateral propagation does increase with airflow rate, but it's not a linear relationship.